Hello viewers, welcome again to another reading session of article Randomly Coupled Multi-Core Fiber Technology. Since this article is lengthy, so we will cover in parts. So let us start. So this article as title suggests that randomly coupled multi-core fiber technology. So let us see what is this all about. So these are the list of authors you can see and start from abstract. Randomly coupled multi-core fiber technology has come to attract lots of attention because of its strong applicability to long-haul transmission system. So this technology is for long-haul transmission system. Compared with weakly coupled multi-core fiber with independent cores, it can simultaneously realize higher spatial channel density and ultra-low transmission loss using existing ultra-low loss single-mode fiber core design. So basically, this is the advantage of this technology that is called randomly coupled. Now comparing it with weakly coupled multi-core fiber. So there are two technology, weakly coupled multi-core fiber, and here it is proposed as randomly coupled multi-core fiber. So with that respect, with these two, we are comparing what is in what term randomly coupled multi-core fiber is advantageous. So it is telling that higher spatial channel density and ultra low transmission loss. Means transmission loss is less as well as its capacity is more. Now next, the strong mode coupling characteristics of randomly coupled multi-core fibers can provide favorable optical properties such as suppressed accumulation of modal dispersion, mode dependent loss, and nonlinear impairments. So three things are there. So because in randomly coupled, they are strongly coupled modes. So that leads to three advantages. One is this modal dispersion, reduction in the modal dispersion. Second one is the mode dependent loss. And third one is the non-linear effects. Means non-linear impairments can also be reduced compared to the weakly coupled multi-core fibers. Now, this article gives an overview of randomly coupled multi-core fiber advancements. First, we describe the classification and design of randomly coupled multi-core fibers and explain what the randomly coupled multi-core fiber are. So what is this technology all about and how they are designed. So first defining and then how they are designing. So design technology, design method or design process have been also explained. Next, the state of art randomly coupled multi-core fibers can accommodate 4, 7 or 12 cores in a standard 125 micrometer cladding while achieving ultra low transmission loss and or small modal dispersion, which are very promising for long haul transmission medium. Actually, why this is talking about this standard 125 micrometer cladding, because that is the commercial fiber dimension where cladding dimension is 125 micrometers, so that you can design a standard couplers to couple two fibers. So this outer region is fixed, dimension of outer region is fixed. Now within that outer, how many cores you can accommodate, that how many cores you can accommodate. So state of art facilities provides 4 number of cores, 7 numbers of cores, or 12 number of cores in different topologies. So these are the things. Now, next we present the methods to characterize the optical properties of randomly coupled multi-core fibers and the difference compared to conventional single mode measurements. So now this randomly how to characterize these properties, how to determine the quality. So these things have been explained. We also show the low MDL mode dependent loss conductivity of this type of multi-core fiber and the capability that can suppress modal dispersion. A field deployed randomly coupled multi-core fiber cable testers is also presented, means actual case, which confirm the favorable optical properties and randomly coupled multi-core fiber after deployment. Then multi-core amplifier technologies are briefly summarized. So beside fiber amplifier also. And finally, we discuss the performance improvement in the transmission over randomly coupled multi-core fiber and suitable application area. So keywords are erbium dot fiber amplifiers, optical fiber communication, optical fiber, space division multiplexing, SDM. Introduction. Network traffic has been growing exponentially over the decades due to repeatedly emerging digital applications and services such as cloud services, video streaming, and most recently the Internet of Things, that is called IoT. And transmission capacity through single mode fiber has also exponentially increased to tackle ever-growing traffic demands thanks to various technological innovations such as wavelength division multiplexing and higher order modulation with digital coherent technology. So one, two, three. So these are the few technologies which are which are able to give the services, which are able to meet the exponential bandwidth demand as well as high data rate. So what are those technologies? WDM technology, that is called wavelength division multiplexing. Then higher order modulation formats like QPSK, BPSK, then 16 QM, 64 QM, like that. So by increasing this modulation formats, higher order modulation formats, as well as coherent digital technology. So these are the few technologies which are making, making feasible these processes. However, single mode fiber capacity is now approaching its fundamental limit, and in the efficient amplificable wavelength band. Now, what is the draw? What is the limitation? Because currently single mode fiber is now approaching to fundamental limit. Means it is already saturated. Utility or the available bandwidth in the single mode fiber is already saturated, already exploited. Now it is not able to further meet the demands. So to tackle this limitation, space division multiplexing, that is SDM, has been extensively researched and various multi-core fibers and few mode fibers have been proposed for SDM transmission. So now say single mode fiber is now becoming limiting factor. So that is why we are going for multi-core fibers as well as few mode fibers. So these are the two things. Space division multiplex, in which we suggest nothing but a multi-core fiber in a given cladding, as well as in which we and another one is the few mode fibers have been proposed. Today, SDM is recognized as the only practical way to multiply the transmission capacity of optical fibers. So SDM, that is the space division multiplexing in a single in a cladding. If we increase the number of cores, earlier it happens to be only one core, and this is the cladding. Now we multi-core. Another Among the various space division multiplex fiber, randomly coupled multi-core fibers are one of the most promising transmission media for long haul transmission. So now within multi-core, what should be the coupling mechanism? So one is this weakly coupled, and another one is the randomly coupled. So let us see what is this weakly coupled, WC, and RC, that is the randomly coupled, which is intentionally, now this RC coupled, intentionally designed to have random mode coupling between the multiple cores. So now mode coupling is random in nature. By permitting random mode coupling, randomly coupled multicore fiber can simultaneously realize ultra-low loss and high special channel density. So 11 and 13. 11 to 13 means reference number 11, reference number 12, and reference number 13. These three papers have already worked on randomly coupled. So it is not fixed. So there is a random coupled idea. So for time being, let us see what are those papers. 11, 12, 13, because that paper is first paper which is from the core theme. So this paper is lengthy. So let us see. 11 is here. T Hayashi, and title is Record Low Spatial Mode Dispersion and Ultra Low Loss Coupled Multi-Core Fiber for Ultra Long Haul Transmission. So 2017, and 12 number is micro bending behavior of randomly coupled ultra low loss multi-core fiber, and 31 is T Sakamoto et al. Twisting rate controlled 125 micrometer cladding randomly coupled single mode 12 core fibers. So it was published in 2018. So these are the three articles which are on randomly coupled. So coming back to the text where we left in the introduction section. So let us see. Yeah. Random mode coupling is also beneficial for suppressing the accumulation of modal dispersion, which have been reported in so many articles like number 14, 15, 16, 17, 18, 19, and 20. So that is called modal dispersion. So how this random mode coupling reduces the modal dispersion have been extensively reported in these articles, reference number 14 to 20. Next advantage is that mode dependent loss. Randomly coupling is giving the again mode dependent loss, means reduction in the mode dependence loss, that is called MDL. And results related with this means research related that randomly coupled random mode coupling gives mode dependent loss lesser in quantity, or research on this aspect have been reported in 20 to 25. So again, 6 papers are there. Here, 7 papers are there for this aspect, MD aspect, that is the modal dispersion effect. Another one is mode dependent loss. This is the dispersion and this is the loss. So MDL. So 7 paper here and 6 paper here. So about 13 papers have been uh, included to address these two issues. Now, third issue is that non-linear impairment. So whatever they are telling, that randomly mode coupling gives the advantages of lesser mode dispersion, lesser mode dependent loss, as well as it addresses the issue of non-linear impairments. So that aspect has been reported in the article 24, 26, and 27. So I do not know this 25 is excluded. So maybe on other topic, but these three articles is addressing non-linear. So three things, three important advantages of randomly coupled multi-core fibers are: first, it is modal dispersion, mode dependent loss, and non-linear effects. And reducing the non-linear effects. So these are the prominent advantages, and this fact have been established in the research domain with the publication of about 13 here, 14, 15, 16. So total 16 article you can say have, is addressing these three issues. Although multi-input, multi-output, that is MIMO, digital signal processing is necessary for undoing mode mixing among the cores, ultra-long haul transmission over greater than 12,000 kilometers using offline processing given in 2428, and real-time 7,200 kilometer transmission using online processing on a field programmable gate array, that is FPGA, have been demonstrated. So in 29, article number 29, real-time using FPGA and DSP, MIMO and DSP have been used to undo the mode mixing among the cores for long haul transmission. So that are reported in 2425. So wideband, now they are using DSP technologies also and FPGA also at the receiving end to address this issue. Now, wideband transmission experiments have also been performed in the C and in the C plus L band. So far as band is concerned, so these two article 30 and 31, they are taking care of wideband issues. Now, next, this article gives an overview of randomly coupled multi-core fiber technology. First, in section 2, we briefly discuss the classification of multi-core fibers to understand what randomly coupled multi-core fiber discussed in this article are and what is different from other types of multi-core fiber. So definition and classification and differences is given in the section 2. Section 3 discusses the multi-core fiber designs to assure random mode coupling and the effect of fiber bends and twists on group delay spread, and introduces representative examples of reported randomly coupled fibers. So now how to achieve this randomly coupling in multi-core fiber? What are the method? How to design? That aspect have been given in the section 3. So section 2 describe what is it multi-core and what are the different types, classification, definition, and types. Section 3 discusses how to design aspect. Now, section 4 describes how to characterize randomly coupled multi-core fiber. Now, section 4 describes about characterization methods. What parameters should be evaluated in a mode averaged or mode resolved manner, and what methods should be used in their measurements. So, how to characterize? So here, this is the design aspect. There is a characterization aspect. There is a definition and differences. So section 1, section 2 about definition, classification, differences. Section 3 about designing, achieving those design aspects. And section 4 describes about the characterization methods on what parameters we can characterize. Now, section 5 reviews connectivity technologies for splicing and termination of randomly coupled multi-core fibers. So section 5 about how to couple, how to connect two fibers, capability, technology, fabrication results, and world's first field deployment and characterization of multi-core. Now, this is the commercial kind of say, experimental aspect have been covered in section 5. Section 6 reviews multi-core fiber amplifier. Now, I think this section talks about amplifier. Till now, we were discussing about fibers, multi-core fibers. Now we are discussing about amplifier. Technologies applicable to randomly coupled multi-core fiber amplification. Because we need amplifier also. So fiber and amplifier both should be compatible. So that aspect has been taken care in the section 6. Section 7 describes transmission experiments over randomly coupled multi-core fiber, shows performance improvement in non-linear transmission, and also discusses suitable applications of randomly coupled multi-core fibers. Section 8 concludes this article. So with this part first is concluded. We will soon meet in another part. Thank you for attending this reading session.